So what we were discussing in the last time we met was concerning the solution of um, the equations of motion, or setting up the equations of motion so that we can obtain the position and the momenta of a particle or all the particles constituting the system as a function of time, right? So we saw three different methodologies. One is the normal f equal to ma kind of method. The other one is the Lagrange method, and third one is the Hamilton method, right? In this you define this L, which is equal to T minus V, and then you are able to do something like d by dt of dou L by dou Q dot minus dou L by dou Q must be equal to 0. Performing this essentially gave you the equations of motion for a simple problem which we studied. I hope you remember that, right? We studied something like that, and for this problem we had to derive the equations of motion, right? And these were the equations that we could use in order to write down the equations of motion. Then in the Hamilton's method, we defined what is referred to as the Hamilton, which turned out to be the kinetic plus the potential energy in case of conservative systems. Of course, there are a couple of steps that you have to follow in order to write down. There are a couple of steps that you have to use in order to write down the Hamilton. So I hope you can find that in the slides. And for a conservative system, it turns out to be the sum of the kinetic and the potential energy. And then once you have that, you can write down what are referred to as the canonical equations of motions as follows. That's right. These gave us the equations of motion, right? So now the whole idea is we are looking at what is referred to as the classical version of statistical mechanics, right? Statistical mechanics. So for this, in order to motivate the idea behind this, what we say is, let us consider a system of a crystal, okay, where all the atoms are connected by some springs. I think I have a better picture in my slides right here. Okay, you consider a system like that, where you have a large number of atoms, a very large number of atoms, and all of them are interacting with each other through some sort of nonlinear springs. So at a finite temperature, each of these atoms are going to be vibrating about their mean positions, right? So keeps vibrating about their mean positions, right? Now the question is, firstly I would like to mention that it is not necessary that these springs or the interaction between these atoms are always linear springs. There is some complicated interaction that exists between all the atoms in the system, and at a finite temperature they are moving. That means at every instant of time there is a position and a velocity that is associated with all the particles of the system. So the idea of statistical mechanics, in statistical mechanics, the basic idea is that you are able to say that there is some property of the system which is actually a function of the position. Okay, let's use Q for position, the generalized position, and the momentum of all the particles in the system. And if you knew this function A, whatever may be A, right, some property of the system, then you can find some average A. So let us use time averaging. So let us use a different symbol for time averaging. So A bar is the time averaged value. So what did I say here? I think I wrote this expression down as well. So it was limit some delta t tends to infinity, a very large value of delta t, integrate from 0 to say or t naught to t naught plus delta t, a of q of t comma p of t times dq dp, right. So, or rather not dq dp, maybe dt, right, because a becomes a function of time when you write it like this. Now, what are the problems? So you now have some average value for A, and I told you in the last class that when you are trying to measure the physical quantity, then you are actually measuring this time averaged quantity in reality. So the atoms are basically vibrating very fast and they have some temperature that is oscillating about some mean value, but when you put a thermometer there and remove it, the time period for this to actually reach the particular value is very large when compared to the time it actually takes for you to see the mean value, right. So that's essentially the whole idea. So basically this delta t also, well, I told you that it tends to infinity. This infinity is actually not very large when it comes to materials like solids, and it also depends upon the property that you are basically looking at. Okay, it will. So now what are the problems that one can see when you look at an expression like this? So firstly, you have to know what this A. So for example, if I say I want the elastic constants of the system, then I have to have an expression for the elastic constants of the system as a function of P and Q, right? And then I have to be able to evolve this P and Q by solving the equations of motion. I need to know how P and Q change continuously as a function of time, so that I can then plug it into this expression and find the expression for A as a function of time and then integrate it over time and then obtain this average equilibrium value. Now the whole problem is, so there are two issues. So find the expression for A and then solve the equations of motion for this P and Q. So remember, this P and Q are just, what are P and Q? They are the momenta and the positions of all the atoms that is comprising the system, right? It's just a huge, when there are a huge number of atoms, then it becomes extremely difficult for you to solve and calculate how P and Q are moving in reality when you have atoms in the order of 6.023 × 10⁻23, right? It's very hard for you to solve the equations of motion when you have such large number of atoms. However, in the topic that we will be addressing next, which is basically addressing finding out material properties using molecular dynamic simulations, that is exactly what we do. So we construct our crystal structure based on the methods that I have just taught you, and then we solve the equations of motion and trace the positions and the momenta of all the particles comprising the system. And then once we know this function A, then we can perform some sort of a time averaging to calculate the average property, average thermodynamic property of the system that we are trying to look at. But practically, when we talk about statistical mechanics, we don't generally talk about this time averaging, simply because of the fact that it is not theoretically possible for us to evolve the P and Q for a system comprising of 6.023 × 10⁻23 atoms in the order of 20. So statistical mechanics now takes a slightly different approach, okay, takes a slightly different approach, and that approach is referred to what is known as the ensemble approach. Okay, ensemble approach. Okay, what happens here is the following. So instead of actually assuming that you have to track the positions and the momenta of all the particles in the system continuously with time, you imagine several snapshots of the system, each of which is in a different microstate, so but the same macro state. For example, if you have a crystal, okay, with n number of atoms, okay, then you imagine several mental copies of the system, of the same system, okay, a large number of them, and each of these systems have certain PIs and QIs. That means so QI is what? QIs and extends from Q1, Q2, Q3 and so on till Q3n. Okay, PI is nothing but P1, P2, P3 and so on till P3n. That means Q1 is basically the x coordinate, for example, of a particle 1. Q2 is the y coordinate of particle 1. Q3 is the z coordinate of particle 1 and so on, and Q3n would be the z coordinate of the nth particle. Similarly, these things are the x coordinate, x momentum, y momentum and z momentum of first particle, and this one is the z direction momentum of the nth particle. Now, what I am trying to say is, if a macroscopic state is imposed on the system, the values of Q's and P's that the system can take can be different, but the macro state that they all possess will still be the same. So there are so many different ways that the same macro state can be reached through different values of P's and Q's, right? So is this aspect clear? Right. So basically, each element of the ensemble is basically in a different microstate corresponding to the same macrostate. That means the positions of all the atoms and the momentum of all the atoms are changing, are different from one ensemble to the other. However, they all have the same macrostate, that is whatever we imposed on them. So we talk now what is referred to as the phase space of the system. So we can't take photo. So what you do, you construct a 6n dimensional space. Okay, so 6n dimensional space. So this would be, for example, Q1 of Q1 means just the Q2, Q3, Q4, Q5 and so on, P1, P2, P3, P4, P5 and so on, 6n dimensional space. Okay, just imagine it. Hard to imagine, but you can give it a shot. Okay, if you want to simplify stuff in a one-dimensional system of this one, then there is only one position and one momenta. So you have a Q, you have a P, right? This is easy to imagine. But if you have n particles, then I want you to imagine a space where you have axes running for each and every P and Q that the system can actually possess. Now, any point on that space is representing a microstate for a given macrostate. Any given point in that space is actually representing a microstate for a given macrostate of the system, right? Now, each of these ensembles have different points in the phase space, right? And all of them are now moving because P and Q are getting evolved with time. Each of these things are getting evolved with time, right? So you can imagine for a system with a large number of particles, this entire phase space is going to be a swarm of a large number of particles, right? Each particle representing a microstate incommensurate which or matches the macrostate of the system. They are not any arbitrary points. That microstate should be such that it satisfies the imposed macrostate. So, what happens now is several properties of this particular phase becomes useful in defining in helping us formulate the statistical mechanics. So, let me just highlight a few things. I am just going to put P and Q, but it does not mean this is just one particle. There are many particles, and there is just a swarm of so many different particles here. Because these particles are huge in number, very large in number, okay, and they are so close together, this is going to be a little bit of hand waving, but you will see that there is a meaning to this in a little bit, either in this class or in the next class. It becomes useful for us to define an infinitesimal volume element in this phase space, okay, and the dimensions of which are obviously dp power 3n, dq power 3n, a small volume element, right? Okay. Therefore, the total number of points, so we can also define what is referred to as a density rho. So, imagine continuum mechanics, so you are able to define a density which is mass per unit volume, whereas in phase space and statistical mechanics, I will call this density as number of points per unit volume of the phase space at any given instant of time. Okay. So, this basically rho is basically telling you how these points are basically distributed in the phase space, right. So, this is going to play a very important role in statistical mechanics. So, you have clearly the total number of points in this phase space is obviously integral over the entire phase space rho p comma q t dp dq. Okay. This is okay so far? Are there anything that's any doubts before we proceed? Okay, fine, very good. Okay. So, now instead of saying that I am going to take a time average of the quantity that I am interested in, I am going to tell you that I am going to take a phase average of the system of the quantity that I am interested in. So, for example, the same quantity A, if I want to take the phase average, what I would essentially do is the following. I would say it's A, but now A is only a function of P comma Q, okay, P and Q may be functions of time, rho P comma Q So, this actually gives me the phase average of the quantity A, correct? So this tells me, so this quantity, if you look at it, it is telling me, what is it telling me? This is the total, this is the density at that particular point P comma Q, right, divided by probability per unit volume that I can find a point at P comma Q, right? That's what it's telling me, correct? Probability per unit volume. So this entire quantity is basically telling me what is referred to as the phase average of the quantity. Now this and this are different. This is time averaging, this is phase averaging. Okay. Now the whole point is, in writing my expression this way, there is a functional dependence of this rho on t. That means t could explicitly depend on time. The total number of points that is present per unit volume in that phase space could actually vary with time, is what that expression is telling you, right? So this average quantity could also vary with time, right? Yes or no? This average quantity could also vary with time. Now if I am talking about a system which is in equilibrium, do you think this average quantity should vary with time? No, right? If a system is, my goodness, previously the AC was not there, but can we increase it to, okay, so this average quantity A cannot vary with time if we are talking about a system which is in equilibrium, right? So the only thing here that actually depends on time explicitly in the way I have written it is this rho, right? So if rho does not explicitly depend on time, that is, number of points per unit volume in the phase space is such that it doesn't explicitly depend on time, then that rho is a good candidate to describe systems in equilibrium, right? That distribution is a good distribution, is a valid distribution to describe systems at equilibrium. Okay. Is this okay? The average doesn't change with time. Yeah, if this has to be true if dou A by T must be 0, isn't it? That is different. Let us not talk about non-equilibrium thermodynamics, that's now complicated, right? We will talk about equilibrium systems, systems at equilibrium. So rho being not being explicitly dependent on time is a valid distribution the system can have if we want to describe systems at, when we want to talk about systems which are at equilibrium, right? A few properties of the phase space. So rho is a function of P, Q, T in general, and what is the material derivative of rho with T? Students who have studied advanced mechanics of solids, transport phenomena, so what is it? Dou rho by dou T plus something you said, grad something. Grad? Correct. Tell me. Rho divergence of rho, correct? But V is what here? Okay. You remember this? Do you remember this? Okay. Let us start with a little bit of. If P is a function of this, then you had dP by dt is equal to dou P by dou T plus dou P by dou Xi times dou Xi by dou t.
Material derivative equal to partial derivative plus u dot del.
Okay, that's fine too. Dou p by dou t plus dou p by dou xi, because p is a function of this xi, right, which is nothing but gradient of p dotted with the velocity, right. You have studied this before, you have seen this before, right. So I am going to write it down for this row, that's it. Okay, let us, there are more, there may be better derivations to do, but that is not needed for what I am trying to get at. So d is it right? D rho by dou t is nothing but dou rho by dou t plus summation I equal to 1 to 3n, because now I am not talking about rho as a function of x, y and z, rho is a function of q, p and t, right. So I have dou rho by dou qi into qi dot plus dou rho by dou pi into pi dot. Is that right? Yeah, okay, good. Anybody who has not seen this before at all? You have not seen it? Transport phenomena, continuum mechanics, material derivative you have not seen. Okay, fine. So you will eventually learn this. Okay, this is actually a very simple stuff. You will learn it. Well, it's not simple. You will learn it. Okay. There's a lot of things that goes into actually writing this down. But look at it from this perspective. I am taking a total derivative, but it involves a partial derivative plus partial derivative with respect to time plus partial derivative with respect to q, and then the derivative of q with respect to time plus partial derivative of rho with respect to p, and then again p with respect to time. Okay, somewhat intuitive, but it can't be derived so easily. Okay, so the thing is, what does this physically represent? If you have taken again continuum mechanics, how this number of points is changing with respect to time for an observer that is traveling along with that point, right. If you are talking about, if you have derived a mass balance in transport phenomena or in continuum mechanics, that's essentially what it means is, if you are sitting on a volume element, and what is that, in Eulerian and Lagrangian, all those things, yeah, so you can derive that based on that. So if a person is sitting on a particular volume element in phase space and traveling with it, it is telling you how many the rate at which the total number of points inside that volume element are changing with respect to time. Okay. Now these are the points that are there in the phase space are all coming from the Hamilton's equation. There are no new points which are going to be generated all of a sudden, or the existing points are not going to vanish from the system. There is no reason for us to believe that that is going to happen. Therefore, the total number of points that is there with the person who is actually traveling with that volume element is going to remain the same. Okay. Therefore, this quantity is 0. It is similar to your mass balance idea. Okay. Basically, the points in the phase space move like an incompressible fluid. Okay. This is different from this, obviously. d rho by dt is equal to 0 is a fundamental property of the phase space, whereas dou rho by dou t is equal to 0 may or may not be true. If you are talking about systems in equilibrium, then dou rho by dou t is actually equal to 0. Otherwise, it need not be 0. Now, if dou rho by dou t and d rho by dou t have to be 0, if d rho by dou t is 0 anyways, okay, and dou rho by dou t has to be 0, has to vanish, then this quantity here has to be 0, right? One yes,
So over the volume, rho average should be at 0, right?
rho average, which one?
Like d rho by dou t should be 0.
This one,
Yeah, for a particular volume element,
particular
there will be
point,
rho
it is at a point, it is an incompressible fluid flow. So if d rho by dt is 0 anyways and dou rho by dou t has to be 0 for our system at equilibrium, then the only condition that rho has to satisfy is the fact that this quantity here must actually be equal to 0, right? So there is nothing we can do to q and qi dot because they are just the positions and the velocities of all the atoms in the system. But what can you say about rho? When will this be 0? Under what conditions can this be 0? What can rho be so that this is 0? Right now rho is a function of p, q. What if it's a constant? Right? If rho is a constant, it doesn't depend on p and q. At every point, it doesn't really depend on p or q, then it is 0. So rho equal to a constant value is a candidate distribution for systems at equilibrium. And it so happens that if rho is a function of h, explicitly h, is a function of p and q only through h or the Hamiltonian, even then this quantity becomes 0. For example, if you take a look at this, I is equal to 1 to 3n dou rho by dou h multiplied by dou h by dou qi into qi dot plus dou rho by dou h into dou h by dou pi. I am saying this is 0, which it is because if I qi dot is nothing but dou h by dou pi according to the equations of motion, and this one dou h by dou pi, and pi dot is nothing but minus of dou h by qi equal to 0, right? If rho is a function of p and q only through h, through the Hamiltonian, even then this quantity becomes 0. Okay. It so happens that this distribution describes the micro canonical ensemble, and this one describes the canonical we will see how it turns out for this. So you will figure out that this rho is nothing but e to the power minus beta h by beta h, where beta is nothing but 1 over kt. We will, or proportional to, rho will be proportional to e to the power minus beta h or beta e. E is nothing but the energy. H and the energy are the same for conservative systems. Okay, we will show this probably in the next class. So what did I? So quite a few things we have looked at. So I just want to have a recap because some of these things might seem a little bit unrelated to what we have been talking so far. The whole idea is to see whether we can obtain these expressions A using statistical mechanics, so that we can, once you obtain A as a function of P and Q, and then you will be able to use molecular dynamics simulations to calculate these quantities. Okay, and in molecular dynamics you always use this time averaging in order to calculate these quantities. However, in reality, not in molecular dynamics, in reality it becomes difficult for us to evolve a P and Q with time. Therefore, we resort to what is referred to as a phase space approach, and the phase space basically consists of a large number of points in the phase space, which is consisting of this P and Q, and each point is representing a specific microstate. Okay, and the points are all so close together that it so happens that at a particular point P comma Q, you can define an infinitesimal volume element dptq, and then you can define a phase average like that, and you can define a density like that. Okay, and this phase points in this phase space are all moving. They're all moving because they are moving in accordance with the Hamilton's equations of motion, right? So dou rho by dou t, so the value of this density may be varying with time. Number of particles per unit volume may be varying with time. However, we know that the phase average should physically, for a system at equilibrium, the phase average should not change with time. So we make the argument that is possible if this density function is also not explicitly dependent on time, right? And we derived this, or we didn't derive it, we wrote down an expression to show that, or suggesting that the particles in the phase space are moving like an incompressible fluid. Okay, and which means d rho by dt is 0. If we want our system to be representing a system at equilibrium, then we are able to derive some simple properties that this rho should have. That's the whole idea. Rho should be a constant, or rho should be explicitly a function of h. Okay, we can show through another analysis what this function is for the canonical ensemble. Okay, and we will do that in the next class. Okay, but now, since there's a little bit of time left, I just want to talk about something simple. So let us consider an ideal gas, a system of ideal gas, right? It contains maybe n particles. Okay, what will be the what would be the total number of particles in the system? How would I calculate it? Total number of particles in the system is total number of microstates, right? That is okay with you? Total number of particles in the phase space is nothing but the total number of microstates possible microstates, right? The system can take at equilibrium. That omega that we saw from the quantum mechanic, this number of particles should also give us that information, right? Because there's so many points, but there may be gaps. It's not going to form a lattice.
So if there are gaps, then how can we make this clear?
Which one? You don't integrate where rho is 0. That's it. You don't integrate where there's 0. You put rho equal to 0 there.
But there's no rho in this.
In this there is no rho. In this you don't have to worry. So you have a large number of points. D Q over 3. These are the possible. What is this? Is going to give you the total. Do you agree that this is going to give you the total number of points? Total volume of the phase space. And if I have omega naught, which is actually a fundamental volume element, that will give me the total number of points. Yes or no? Yes. So now let us consider an ideal gas, the same thing that we actually looked at previously. Okay. In that case, if you perform this integration, Q is basically the positional coordinates, x coordinate, y coordinate and z coordinate of my particles, right. So each dq1, dq2, dq3, if I integrate over the entire volume of the phase space, is going to give me the volume that gas is can actually occupy, right. So this thing is actually V to the power 3n, because every 3 dq's is contributing to one volume, right. Sorry, V power n, because every 3 dq's is contributing to one volume. Is that right? I think I have lost most of you. This makes sense? Yes? Now this one, I am supposed to integrate over all the possible p's that it can have, right? However, the p's are supposed to be such that this must be equal to E star, because you are talking about an ideal gas in a confined volume and at a specific energy. Right? Yes or no?
How did we split the integral?
Which integral? This is not what is the issue. So let us take a simple system. So if you have only one particular atom in your one particular atom of gas in your box, then you have dqx, dqy, dqz, dpx, dpy, dpz. This is the only possible thing, and this is actually over the entire or over all allowed possible values of p and q. So I can actually split it separately because there is nothing else here, right? Can I split it or not? You're not convinced that you can split it?
P is
Huh?
P.
P.
Split it into three parts. dqx, dpx can be split separately.
The x components,
X
the y
components can
Why?
be split
Why?
because
the interdependent between the
those two
Which one?
elements-
No, now in Hamiltonian formulation, q and p are independent variables. That is the whole idea of the Hamiltonian formulation. Right? You are saying that p is nothing but q dot. No.
some time derivative relation.
No. In Hamilton's formulation, p and q are independent variables that you get. Right? They are not dependent on each other. They need not be treated as being dependent on each other.
So even say
They are
qx, qy won't be dependent on each other.
no. Why? They are independent quantities. They are independent quantities. So you can split. Okay. Now this, have you seen something like this before? You have seen this before. In Schrodinger's wave equation, for a n particle gas system, instead of px and py, you had some nx, ny, nz squares and so on and so on and so on, right? And it was equal to some E star, right? And this looked like the equation of a hypersphere, and you calculated the volume of the hypersphere. Yes or no? All that you did. You can do the same analysis in this. Okay, you can do, you remember that or not? If you are not remembering that, I cannot, you remember that, right? You can do exactly the same analysis here to find out the volume in the shell with energy between E star plus half delta E star and E star minus half delta E star. We did this analysis in great detail when we were actually looking at the quantum mechanical system, right? So this exercise you should be able to do. Okay, so this is not a very complicated thing. You can easily do it. Okay, what I wanted to show you is the following interesting aspect. Okay. This omega, this is what I wrote down here. This omega is the is the total number of microstates available to the system, and there is nothing but this small omega, which is the total volume under the phase space, divided by omega naught, which is a fundamental volume element, and this omega can be written like that, and then this happens to be v to the power 3n and this d3n or d3np is that large expression that I just wrote, which is essentially calculating the volume in the spherical shell having energy between E star plus half delta E star and E star minus half delta E star, and that gives us the following omega. Don't worry about the derivation. If you are not able to do the derivation, don't worry. It's not important for this what I am about to highlight. Okay, but this is what you will get. You will get that expression right there, 38. Okay. The only difference between this omega and the capital omega, or sorry, if you want this capital omega, okay, the total number of microstates, then omega has to be divided by some quantity, and that quantity turns out to be h to the power 3n. The ratio omega by omega naught, where omega is this and omega naught is h to the power 3n, gives us the actual quantum mechanical microstates. There is no other way you can actually derive the total number of microstates from a classical mechanical means, because h is simply not there in classical mechanics. Planck's constant. The expression here, which is why this is interesting. So this expression 38, when you compare it to equation 17, differs by that h power 3n only. So if you want to obtain the right number of microstates, you have to divide the classical mechanical volume by h power 3n. Now, this is still even more interesting to me, because what is this? Have you heard of Heisenberg's uncertainty principle? You have heard of that. So it says that it is impossible for you to specify both the position and the momenta of a particle, and the uncertainty will be in the order of Planck's constant. But what did we do? In the classical thing, we put a arrow mark and said there is a point p comma q. We put a cubic volume element of size dp, dq and did all these things. Our analysis is telling that the error that we have made in actually identifying that point is actually in the order of h. So the whole, so I know that during the beginning of the class it was getting a little bit weird. I don't want you to understand those weird things. I just want you to keep in mind that the dp dq that we did there is okay, simply because of the fact that you cannot specify both the position and the momenta of the particle beyond, there's some uncertainty associated with it, which is in the order of Planck's constant, and you get that here. So the quantum mechanical microstate is related like this, and you will have the h power 3n, and of course another factor called n factorial for taking care of the fact that you want the particles to be to consider for the fact that the particles are actually indistinguishable. We did this also, right, for the classical, for the quantum system, right. So around point pq in phase space, you have to assume that there are many points which actually can be treated as the same pq, simply because there is an uncertainty in specifying this p and q. Okay, so even in classical statistical mechanical quantities, you will often encounter a denominator with h power 3n and this quantity with n factorial to take into account for the fact that there is an uncertainty in the specification of p and q, and there is indistinguishability of the particles. Just because it's classical, it doesn't mean this h does not appear. There is no other way to get the correct value from classical statistical mechanics. You have to compare it with the quantum. Okay. So this is what I wanted to tell. So the basic, the goal of today's class was just to highlight this h power 3n and phase space. Tomorrow's class, we will show that this rho depends explicitly on h for the canonical ensemble. Okay. I will do some very simple derivations, and then we will derive the Helmholtz free energy as a function of h for the system, and then I will leave you with the motivation that if you know the Helmholtz free energy, you are basically done. Okay. Of course, mathematically it can get complicated. You, for example, if you know the Helmholtz free energy as a function of position and the velocities, if you know the strain as a function of position and velocities, then you can actually differentiate them. How, I don't know. You can actually theoretically differentiate the Helmholtz free energy with respect to the strain to get stress. You can differentiate it one more time to get the young elastic constants and all that you can do. So that is the spirit of this portion of the class, just to bring it to the point, tell you that once you find this A as a function of P and Q, and you find your strains as a function of P and Q, you can actually get all the thermodynamic properties of the system. And then, since we can't do everything in statistical mechanics in this class, we will then start doing some molecular dynamics simulations, which I think many of you are waiting to start learning. Okay.